I hope you enjoyed this short video right before this one that shows you different kinds of star sizes. It's kind of one of my favorites. So we're going to talk about stars, and we're going to start with this learning video to learn about what kinds of stars there are out there. In the next video, we'll learn why there are those different kinds of stars. So we're going to talk about three things: distance, brightness, and color. These are things that we can measure for stars. Let's start with distance. Distance is measured by the method of parallax. And we've talked about this when we talked about Tycho Brahe trying to find stellar parallax, which he failed to do because he didn't have instruments to help him measure the very, very tiny angles that he needed. Remember that parallax is the apparent shift in a star's position because Earth changes position. So here are distant stars, here's a nearby star, here's Earth going around the sun, and in December, we can line up that star with the distant stars, and then 6 months later, we can line up that same star with distant stars, and it appears to line up differently because of our motion, and that angle is called the parallax angle. And remember, the largest parallax angle is 1/3600th of a degree. That's very, very tiny. Another thing about distances is that distances in space are so enormous. We really can't use miles, kilometers, or even AU. They're just not very useful. Instead, we use a light year, and that is a distance that light travels in 1 year. A light year is not a time, even though the word year is in there. To give you an idea for how fast light travels, if I shot a gun at light speed, it would go around the Earth 9 times and through me before I could get out of the way. So that's kind of an analogy for the speed of light. It's extremely fast. Here's a problem that I want you to try to solve. And this is an example of something that could be on your exam. I'm not going to give you a lot of math, but I'm going to give you a little bit maybe here and there. Hit the pause button, see if you can figure this out. All right, so let's approach this problem as you should approach all word problems. What do we know and what do we want to know? Well, we know the distance. We've been given a distance. We've also been given a speed. And we're asked to find a time. So do you know any equations that involve speed and time and distance? Well, this is one of the equations that I require you to know for my class. Speed equals distance over time. I'm going to abbreviate it with letters. S equals d over t. Now this equation would be fine if we were trying to determine speed, but we already know the speed and we want to determine the time. So we need to rearrange this equation to get time all by itself on one side of the equal sign. So we can multiply both sides by t, and that gives us t times s equals d. Then we could divide both sides by s, and that gives us t equals d over s. Some of you have no problem rearranging variables. Some of you are challenged by this. Remember, there's a great website called The Math You Need When You Need It that helps you with rearranging variables. So now we have our equation and we can plug in our distance and our speed, 93 million miles over 186,000 miles per second, and that turns out to equal 500 seconds. The miles divided by miles drop out, and seconds, which is in the denominator of a denominator, pops up to the numerator. Now I asked for the answer in minutes, so you need to convert 500 seconds into minutes. So it takes light about 8.3 minutes to travel from the sun to the Earth. That means when you watch the sunrise, it actually rose 8 minutes ago, but the light is just reaching us. Or if you watch the sunset, it actually set 8 minutes ago. Okay, we're going to talk about brightness now. Brightness is controlled by 3 factors. You could pause the video and think about this. What would affect how bright a star looks from Earth? Size is certainly one factor. The larger the star, the brighter it's probably going to be. The temperature, the hotter the star, the brighter it's going to be. And then the distance from Earth. Some stars are going to appear bright only because they're close. We're going to use the concept of luminosity to describe brightness. This is the amount of energy emitted per second. We're going to be using this in the HR diagram in just a moment. Finally, color. We've talked before about how temperature and color are related when it comes to stars. This is Orion, the hunter, if you recognize it. Here's the belt, here's the sword, here's the shoulders. And what you can see in this picture is that there are a lot of different colors. The reason there's streaks is because the aperture of the camera was held open for a certain amount of time. And you can see the colors a little bit better that way, like this red one here is very clearly red. When it comes to things that are hot, most of us think red hot. But in fact, red hot is not hot. Blue hot is hot. So cool stars that are less than 3,000 degrees Kelvin, which is pretty much similar to degrees Celsius, tend to be red. Intermediate stars, somewhere between 5,000 and 6,000 degrees, are yellow, and that includes our sun. Very hot stars that are greater than 10,000 degrees are blue. And remember, we talked about this in the last video when we talked about light. The hotter an object is, the more it emits short wavelength light. So recall we have a red star here called Betelgeuse. It's about 3,000 degrees, so it falls into this category of a cool star, and it peaks its wavelength at the red part of the spectrum. Here's the sun, which peaks at yellow, and then here's a blue star called Rigel that peaks over here in the blue part of the spectrum. Finally, we've come to the HR diagram, the Hertzsprung-Russell diagram. This is an extremely important diagram in astronomy, and you'll have this at your access to use during the exam. This shows all of the different stars that we have observed, plotted on the basis of their brightness, their luminosity, and their temperature. Now there's also something here called spectral class. We're not going to talk about spectral class. It has to do with the absorption lines and how strong the spectra are being emitted. If you want to understand how the designations came to be, O, B, A, F, G, K, M, your textbook has a nice little description of the history of those designations. But for us, we're going to think about this axis down here as temperature. Now notice that the cool temperatures are on the right and the hot temperatures are on the left. So the range here goes from cool to hot, but the cool is on the right and the hot is on the left. A little different than what most graphs might show. Then in the y-axis, we have bright stars at the top, dim stars at the bottom. So the luminosity here is based on the sun's luminosity. So the sun is just going to equal 1, and the sun would be right here. And then up here, if a star is up here, it's 100 times as bright as the sun. If it's up here, it's 10,000 times as bright as the sun. If it's down here, it's 100th of the brightness of the sun. So this way we don't have to worry about units. Let's look at each different part of the HR diagram. First of all, there are the main sequence stars. 90% of all stars are located along this band, including the sun. This is what I think of as a normal band of stars, because down here we have cool and dim, and up here we have hot and bright. So this to me seems like the most logical way you would expect to see stars fall in this diagram. Then there are the red giants and the supergiants, which are in the upper right part of the diagram. There's only a few percent of stars that fall into this category, and they're very bright, but they're very cool. So they're a little odd in that way. Bright but cool, and they're very big. Then we have the red dwarf stars, which are down here. They're very cool, they're very dim. Those two things go hand in hand. These are extremely small and extremely dense. Finally, we have the white dwarf stars over here, and about 10% of all stars fall into this group. They're fainter than the main sequence stars, right? Because luminosity down here means they're dim, but they're very hot. And they're extremely dense, even more dense than red dwarfs. And in the next video, I'll talk about what white dwarf stars are actually composed of. Here's a slightly different version of the HR diagram from your textbook. This one is showing the names of stars and where they fall. And it's also showing the color that they emit in general. What kind of things would I expect you to do with this diagram? Well, I might say, compare the temperature and brightness of Betelgeuse, which is up here, and the sun. And then you would say, well, Betelgeuse is brighter, but it's also cooler. So remember, cool is here and hot is here. Next, we're going to take all these different kinds of stars and place them in an order that corresponds to the life cycle of a star.